Hi everyone, it's Christina, and in this video we are looking at the Edexcel paper 1 from 2018 for A-level maths, and this is question 9. So in this question we have a sketch of an ellipse. So it's a curve with this equation x squared minus 2xy plus 3y squared equals 50. And for part A, we want to show that when we differentiate this expression, we get the following here. So to show that question, so what we want to try and do is differentiate this expression to see if we get the same thing here. So let's have a go at that. Let me scroll down. So we're doing part A here. Let me rewrite the equation of our curve. Y squared equals 50. So we want to differentiate this. Now we're going to use implicit differentiation here. Because we can see that in part A, we ultimately want the differential of y with respect to x. But for example, here in our expression, we have y squared here, xy here. Y is likely to be, or is, in terms of x. But because we have them combined in our terms, we're going to have to differentiate x with respect to x first, and then y with respect to x. Hence why we want to use implicit differentiation here. So let's just differentiate term by term first. But remember, we are differentiating everything. Write it down here. Differentiate everything with respect to x. So the first term, x squared, when we differentiate that with respect to x, that's easy, that's just 2x. And then this second term here, we'll do minus 2, that's just the constant term. We can always pull that out. And then we want to worry about xy. How do we use differentiation or implicit differentiation for that? Well, we're first going to differentiate x with respect to x, which is 1. Don't have to write it, but I'm writing it out so it's very clear that we differentiated this x, and we're keeping y the same. So here we're using the product rule now, because now we're also going to differentiate y with respect to x, but keep x the same. If we differentiate y with respect to x, we get dy over dx. X remains the same because, of course, we're using the product rule and implicit differentiation on this term. So then that second term differentiates to minus 2 brackets 1 times y, which is y, plus dy over dx times x, like that. And then the third term is just in terms of y. So 3y squared, if we differentiate that with respect to x, we're first differentiating the whole term 3y squared. So that means we can bring down the index of 2 and then minus 1. So we get 6y. But then we need to use the chain rule here and then also differentiate our y with respect to x. That's just going to be dy over dx, which is what we want ultimately. Equals, if we differentiate the constant term, it disappears. So that just equals 0. So now let's clean that up and rewrite it on another line. So we get 2x minus 2, that's y plus x dy over dx. So minus 2y minus 2x dy over dx. So I've also swapped around the x and the dy over dx. Doesn't really matter. It looks a bit better like this. Plus 6y times dy over dx equals 0. So now what we want to do to make sure it looks like what we're after in part A is we want to get the dy over dx all on one side and all the other terms on the other side. So we can just pull out the dy over dx and we can factorize it and get it on its own. So then let's try and move these terms onto the right-hand side. So then what do we get? We'll get, put the positive term first, 6y dy over dx minus 2x dy over dx equals 2y plus 2y minus 2x. And so from here we can see, let's just factorize out the dy over dx. Let's pull that out, dy over dx, and then bring in some brackets. 6y minus 2x like that equals 2y minus 2x. Something we can do, you might notice all the terms are divisible by 2. So we can get rid of 2. That 6 just becomes a 3. So then dy over dx on the left is isolated now, and we get y minus x on the right all over 3y minus x. And let's just double check. Is that what we want? Dy over dx equals y minus x all over 3y minus x. And that's what we have here. Okay, so that's part A. And we used implicit differentiation and also the product and the chain rule where necessary.